Educational videos by mmsprogramcivil.com. Please visit website mmsprogramcivil.com for videos. Advantages of flat slab. Flexibility in room layout. Partition wall can be placed anywhere. Offers a variety of room layout to the owner. False ceiling can be omitted. Reinforcement placement is easier in case of flat slab. Ease of framework installation. That is, in case of flat slab, you just have to provide a flat formwork because there are no beams. So placing a formwork is easy and economical. Building height can be reduced. As no beam is used, floor height can be reduced, and consequently, the building height will be reduced. Approximately 10% of the vertical member could be saved. Foundation load will be also reduced. Less construction time is required. Disadvantages of flat slab. In flat plate system or flat slab, it is not possible to have large spans. Not suitable for supporting brittle masonry partitions. Use of drop panels uh, may interfere with large mechanical ducting. Critical middle strip deflection. In flat slab, the middle strip deflection may be critical. Higher slab thickness. Compared to typical reinforcement, uh, concrete to a slab system, uh, the thickness of the flat slab are higher, right? The thickness of flat slab is found to be higher than the regular conventional two-way slab. Flat slab are highly risky in earthquake zone. Okay. Design of flat slab using direct design method. Uh, Actually, there are two methods suggested by the code for the design of flat slab. One is direct design method, other is equivalent frame method. We'll see both the methods. So let us start with the basic. Conventionally, when slab is supported on stiff beam, then design of slab is separated from the design of beam and columns. However, if the beams are absent, it is not appropriate to separate the slab design. A concept of plane frame comprising column and slab beam member is taken in consideration, right? So this is a 3D frame where there are flat slab. Okay, so in case of flat slabs, uh, the whole 3D system is divided into plane frames. This is your interior equivalent frame. This is again your interior equivalent frame. This is your exterior equivalent frame, and so on, right? So similarly, you have to divide uh, in this direction in a number of series of frames, and in this direction also you have to divide into number of series of equivalent frames, right? So this is interior equivalent frame, and this is exterior equivalent frame, right? And this has to be analyzed for the design of the flat slab. So this is some basic fundamentals in case of flat slab, where we divide into a number of equivalent frames, right? 2D equivalent frames, and do the analysis, and then do the design. Flat slab is a two-way type of slab. Okay, all the slab panels should be two-way type of slabs. Okay, that is must. Flat slab itself is a two-way slab. Flat slab is a reinforced concrete slab with or without drops. Okay, so this is drop. Okay, drop are considered to be part of slab, and column with or without column head. Okay, so these are column heads, right? And column heads are considered to be part of columns. Slab panel. Slab panel is the part of the slab bounded on each of its four sides by the column center line. Okay, so we can see that this is the center line of the columns, right? Okay, and the this portion which is bounded on its fourth side by the center line of the columns is called as slab panel. So this is slab panel, this is a 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 slab panel, okay. And all this slab panel has to be a two-way slab, right? Okay. Each slab panel is divided into column strip and middle strip as shown in figure below. So over here, this is a line passing through the center of the slab panel. This is another line passing to the center of this slab panel, okay. And this forms an equivalent frame, okay. This is also known as slab beam member, okay. And this is the width of the slab member, that is L2, okay. So this is the slab beam member, okay, which is shown over here, right? Now, how to decide the width of the column strip? So from the center of the column till here, this width that is to be taken is 0.25 L2 or 0.25 L1, whichever is less. This is L2, this is L1, right? Similarly, this also has to be 0.25 L2 or 0.25 L1, whichever is less, right? So this total will give you the width of the column strip. Okay, so once you know the width of the column strip, so L2 minus column strip divided with 2 will give you half middle strip and half middle strip, right? So this is the width of the column strip. This is L2. L2 minus column strip divided by 2 will give you the half middle strip and half middle strip, right? So this is how the equivalent frame, or you can say the slab beam member is divided into three parts, that is half column strip, two half column strip and one sorry, two half middle strip and one column strip, okay. The primary difference between the conventional frame and the equivalent frame lies in the width of the slab beam member. In case of conventional frame, the whole beam rests on the column, and so beam and column both undergo the same rotation, okay, at the joint. So this is our conventional frame where the width of the beam is equal to column or is less than column, okay. In this case, both beam and column undergo the same rotation at the joint, okay. The rotation, they both will go undergo a same rotation, okay. In case of equivalent frame, uh, s- some part of the slab beam falls, only some part of the slab beam falls on the column, and thus the rotation of the slab beam will vary along the transverse section at the column support, okay. The column and its immediate vicinity, blue shaded portion, is shown in figure below, and the part of the slab beam only will undergo the same rotation, right? So this is the width of our slab beam member. This is our slab beam member, right? So only a part of the slab beam member falls on the column, right? So some portion in the immediate vicinity of the column, okay, that is shown in this blue shaded portion, okay, that and column will go undergo the same rotation, right? Now, as we move towards transverse direction, okay, the rotation will change. The rotation will vary, right? This is a very flexible member, okay. So the rotation of this and this will depend upon the unbalanced moment, okay. So that is why, in case of flat slab, the rotation varies along the width of the slab beam member, okay, in transverse direction. Okay, so this in turn results in torsion in the portion of the slab transverse to the slab and passing through the column, and it is called as imaginary torsion member as shown in figure below. This unshaded portion is shown over here in blue, right? So it is assumed, it is found that this strip is supported by this column, okay, and the remaining portion is supported by this imaginary torsion member. So this is how the flat slab action acts, okay. Variation of moment in two-way slab panel, okay. Although the horizontal member in the earthquake, sorry, although the horizontal member in the equivalent partial frame is a very wide beam, it is actually supported on a very limited width of the supporting column. Hence, the outer portion of the member are less stiff than the part along the column line, and distribution of moment across the width of the member is not uniform, unlike the beam fully falling on the column in a conventional plane frame, right? So it is but natural we can feel the region of slab along the central line of the column. Okay, this will be more stiff than the portion outside, right? So that is why this part will take higher moment when compared to this, right? Because this is going to be less stiff, right? That is what is explained over here. Portion of member are less stiff, outer portion, right? These are the outer portions, right? They are less stiff. So as they are less stiff, they will resist a lesser moment. Okay, so this is the bending moment at the center line of the column. This is the bending moment diagram at the edges, right? Okay, and the probable variation of moment in a typical panel of equivalent frame is shown below. Okay, so we can see this is going to take the maximum moment over here near the center line of the column. This is going to take the minimum moment, right? So as we move toward the center of the span, the moment capacity, moment resisting capacity varies something like that, right? Okay, so minimum over here, maximum over here, minimum over here. So this is a very complicated situation. So code has made some assumption and have made things easy for the design of the flat slab. Uh, it is difficult to predict the actual variation of the bending moment, and hence uh, approximation is made, which is achieved by dividing the equivalent frame into a column strip and two half pedal strip, right? So that is why, for this reason, to avoid this uh, uh, to avoid this complication, code has divided the slab beam member into three parts. That is, one is column strip, and you have two half middle strips, right? The total moment on the equivalent strip is then appropriately distributed uniformly across the column strip and two half middle strips as shown in figure above, right? So instead of this variation, okay, code has divided this slab beam into three parts, and then you can assume a uniform bending stress distribution along the column width and along the two half middle strip, and this is what you will take in design, and this makes our work easy for the design of flat slab. Okay, so this is the basic fundamental, or you can say this is the basic reason why we are dividing the slab beam member into three parts, so that we can take a uniform uh, average bending stress distribution in half meter strips and the column strips, right? Following are the recommended methods suggested by IS 456-2000 for determining the bending moment in case of flat slab. Sorry. Direct design method and equivalent frame method. First, we will see direct design method. Following condition must be satisfied by a two-way slab system for application of direct design method. First, there must be at least three continuous span in each direction. Sorry. So there should be at least three spans. Over here we have 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. You must have at least three spans in both the direction, right? So we have 5, so it's okay. Each slab panel should have a significant two-way slab action. Okay. So as I have explained above, each slab panel should be a two-way slab. So this is very important. Okay. And next is the column must not be offsetted by more than 10% of the span from either axis between the center line of the successive columns. So usually in practical field, the center line of the column in both the direction are kept same, right? You can see the center line are kept same. But if say if you want to offset the column, then it should not be 10% of the more than 10% of the span, right? So next point is the successive span length, that is center to center of the support in each direction, must not differ more than one third of the longer span, right? So, so these are the five different spans, okay? Then this span should not differ more than one third of the longer span, okay? That is what code means, okay? The factor live load must not exceed three times the factor dead load, okay? So this is very important. This method is only applicable to gravity loads. This is very important, okay? There should be no lateral loads such as earthquake force or wind load, etc., right? Okay. The type of loading allowed is only UDL, okay? Live load and dead load are applied to all the spans. This is very important point, okay? So let me explain you what does this mean. So in this DDM, okay, we will apply the dead load and live load to all the spans actually. But we know that for getting the maximum positive and negative bending moment, we apply live load either on alternate span or a live load on adjacent spans, right? But in case of DDM, we have to apply live load and dead load on all the spans. So there are chances that you will not get actual critical positive moment. And so for that, the code has suggested a factor beta C, which we will see in detail as we move further. Okay. Okay. So these are some important limitations that DDM has to be, when you're using DDM, then that has to be fulfilled, right? The direct design method is a simplified procedure of determining the negative and positive design moment in a critical section in the slab beam member using empirical moment coefficients. So empirical moment coefficients are given in the code for DDM. Okay, this method is applicable to gravitational loads only and not for lateral loading condition. For the purpose of calculation, the flux stiffness of slab beam and column in case of DDM are considered to be prismatic. Okay, so this is a very important statement which makes our life easy when we are using a DDM. Okay, so let me explain what does this mean. In case of flat slab, we can have a drop or we can also have a column head, right? But in when you're using direct design method, code says that this the moment of inertia due to this column head and drop can be neglected, and we can take the flat slab as a prismatic member and we can take the column as a prismatic member, right? And we can use the formula for the stiffness, that is K is equal to 4EI by L, right? Because we are considering the column and slab to be prismatic in shape, right? Okay, so total design moment for span, which is further distributed longitudinally. So this is the formula given in the code. MO is equal to capital W ln divided by 8, but capital W is UDL, that is small w that is in kilometer per meter square into L2 into Ln, right? So what is L2 and what is Ln, right? So we can see this blue shaded is the UDL, right? Design load, that is dead load plus live load. Okay, that is our WU. W2 is the width of the slab beam member, which is transverse to L1. L2, Ln is the clear distance between the column. Okay, so if there are no capitals, then it is the clear distance between the columns. If there are capitals, then it is a clear distance between the capitals, right? And so WUL2 into Ln will give you the total load for a particular span, okay, or you can say a panel, okay, and that is your capital W. So when you put replace W by this, then you get this formula, okay, W WL2 ln square by, okay. So W is the factor total load in kilometer per meter square. Ln is the clear span in the direction of MO, measured from face to face of column, capital, bracket or wall, but not less than 0.65 L1. Okay, this is very important. Your Ln should not be less than 0.65 times L1, right? So this is very important. L1 is the center to center distance between the columns. Okay. So now we know Ln, we know L1, we know L2, right? L2 is the span in transverse length of a span transfers to L1, right? So L1, this is transfers to L1, so that is L2. When transverse span of the slab panel on either side of the center line of the support varies, L2 shall be taken as average of the transverse span, right? Okay. So what does this mean? Let me explain. Say suppose this span is 4 meters and this span is 3 meters. Okay, so the spans are different. Then you have to take the average, that is 4 plus 3 divided by 2 is 3.5. So you will take your width of slab beam as 3.5. That is what the code means. Okay, okay, fine. So let's move forward. Okay. Uh, when only drops are present in, then Ln will be taken as clear distance between the column as shown in figure above, because drops are considered to be part of slab, right? And so in many cases we find that there are no capitals, there are only drops, and drops are considered to be part of a slab. So in that case you will take Ln as clear distance between the column, right, as shown in figure, right over here. Okay. When drop panels are used, okay, let me explain. When drop panels are used, and the dead load due to the local thickening of the drop should be taken in account for design. Okay, so when we are providing drops, okay, then you will have to consider the self weight of the drop over here in your loading conditions. Okay, and for this load you have to design the flat slab. This is very important. Okay, longitudinal distribution of total moment. Okay. Once you find your moment MO, this has to be distributed longitudinally, right? This has to be distributed longitudinally. Okay, so this is your exterior panel. This is your exterior panel. This is your interior panel. This is your interior panel. This is again your exterior panel, right? So code has given formulas from which you can find the moments, right? So when you moment at A and moment at C will be hogging moments, okay, and so they will carry a negative sign, and the moment at midspan, that's B, will be sacking moment, and it will carry a positive sign. Similarly over here, D and F will be hogging moment, they will carry a negative sign, and E will be sagging moment and it will carry a positive sign, right? So moment at A can be found by this formula, okay, exterior negative design moment. MO is the total moment which we find from here, okay, and this is how you get this moment at A, right, over here. This is negative, right? Okay, fine. Over here, alpha C is given by this formula, sigma Kc divided by Ks. Sigma Kc is the sum of the stiffness of exterior column meeting at the joint. That is sum of stiffness of this column and this column, right? Ks is further stiffness of slab expressed in moment per unit rotation. That is stiffness of the slab. Okay, fine. Now, moment at B is given by this formula. Okay, MO is a total moment. This will carry a positive sign because this is a sagging moment, right? Similarly, moment at C over here is found by this formula, right? Okay. Now coming to interior span, that is this, right? This is your interior span. Then negative moment at D and F is taken as 0.65 of the total moment, and at center, okay, this is negative because these are hogging moments, and this is going to be positive because it is a uh, sagging moment. So this will be 0.35 of the total moment, right? 0.35 times of the total moment. So this is how the total moment is distributed longitudinally in case of DDM. Okay, fine. Now equivalent frame method. Okay, so this is a 3D frame which is divided into a number of equivalent frames, right? Which is divided into number of equivalent frames. This is one interior frame, there will be another interior frame, then there will be exterior frame, this is an exterior frame. So this is how you divide the whole 3D space frame into number of equivalent frame in both the direction, in this direction and in this direction, right? Okay. The equivalent frame method involves the representation of the three-dimensional slab system by a series of two-dimensional frames that are then analyzed for loads acting in plane of the frames, right? So this is one frame which I have shown over here. Okay, fine. There are no limitations as to when the elastic frame analysis can be used. In this equivalent frame method, there are no limitation. Okay, you can apply any type of loading, and you can get the you can do the perfect analysis, elastic analysis. The bending moment and shear force in an equivalent frame are obtained by performing elastic analysis. Such an analysis should generally be performed for the entire plane frame. You should perform the analysis for the entire plane frame, right? We can apply lateral loads to the frame. If the frame is subjected to gravity load alone, and if the frame geometry and the loading are not unsymmetrical as to cause significant sway, that is lateral drift of the frame, each floor may be analyzed separately considering the appropriate substitute frame. Okay, say if this frame is symmetrical and the loading is symmetrical, and and the little drift is say negligible, then you can design the individual floor by using substitute frame method. Okay, fine. In case of equivalent frame, the loads are transferred through three distinct interconnected elements. One is slab beam member. This is your slab beam member. Columns. So these are your columns, and the torsion member transfers to the frame. So this is your torsion, imaginary torsion member, right? Which is transfers to the frame, right? Okay. Now, in case of equivalent frame, the white slab beam member is partially supported by column, and the remaining portion is supported by the transverse torsion member, who gives flexible restraint against rotation and vertical translation. Okay, fine. So we can see that this strip is assumed to be supported by the column, and the remaining portion is assumed to be supported by this imaginary torsion member, right? So when the load is applied to this imaginary torsion member, they will twist, right? So this is your torsion member. When the load is applied, it will twist something like that, and it will deflect, and it will have a downward translation. Okay, and this, due to this twisting, it will try to rotate this column, right? So that is why the code says that you cannot take the stiffness of this column as 4EI by L, but you will have to take an equivalent column stiffness, that is KEC, which will take in the effect of stiffness of column above and below the floor, and as well as the transverse torsion member. Okay, even the stiffness of this torsion member has to be considered for finding the stiffness of this joint, right? So that KEC is found by this formula, that is KT into sigma KC divided by kt plus sigma kc, where kt is the stiffness of this torsion member and sigma kc is the sum of stiffness of the column at top and bottom of the joint, right? So over here, you cannot simply take the stiffness of the column as 4 EI by L, but you will have to take KEC, right? That is what the code says. Stiffness of member were found by taking in account all the variations in the moment of inertia of the member. This is very important, right? This is what which makes the design of flat slab by equivalent frame method very complicated, because over here we have to take all the variations of the column and slab in account. That is, the moment of inertia of all this variation has to be considered in analysis, right? For performing analysis of flat slab using equivalent frame method, a computer program is required. A drop panel are considered to be part of slab for the calculation of stiffness. Okay, slab are considered to be part of slab. Capitals are considered to be part of column for calculation of stiffness. Okay, capitals are considered to be part of columns, right? The calculation of stiffness factor, carryover factor, and fixed end moment of the slab beam member are dependent on the variation of the second moment of area along the span. Okay, such factors have been tabulated for common geometric and loading configuration in various handbook tables. Okay, some standard tables are available in many handbooks where you can directly get the uh, moment of inertia and all that. Okay, from that table. Okay, now distribution of longitudinal moments between the column strip and middle strip. Okay, now from here the design of flat slip becomes similar whether you are using equivalent frame method or a direct design method. Okay, the difference between the two methods is that the way which we get the longitudinal moments are different. Okay, in case of DDM, we use coefficients. In case of EFM, we do the elastic analysis. Okay. After that, everything remains the same. The procedure for ap- apportioning the factored moment between the middle strip and the column strip is identical for both the design method. Okay, that is direct design method and equivalent frame method. Below figure shows how the moments are distributed to the column strip and the middle strip. Okay, so let us start with the negative moment at the exterior support. This is your exterior support. This is your exterior support. Okay. Okay. So we have two different cases. One, when the column width is less than 0.75 L2. When your column width is less than 0.75 L2, L2 is the width of the slab beam member. This is your L2. Okay. Then in that case, whatever design moment which we get over here, this is our A, right? This is for exterior panel. This is A. Okay. So let us see in the figure. Uh, this is our A, right? So this is our A which we obtained from DDM. Okay. That whole moment will be taken by the column strip, right? You can see, right? And the moment transferred to the half middle strip will be zero, right? Whole moment will be taken by the column strip, and the moment transferred to the half middle strip will be zero. Okay, right? Now, when if your support width is greater than 0.75 L2, then some moment will be taken by the column strip and some will be taken by the half middle strips, right? So the moment that will be taken by the column strip will be width of column strip divided by L2. This is width of column strip divided by L2 into the exterior moment. Okay, the exterior moment which you get over here, right? And the part of moment which the half column strip will take will be uh, 1 minus this divided by 2, right? So that is 0.5 into 1 minus width of column strip divided by L2 into the exterior moment, right? So this is how you uh, distribute the moment to the column strip and the two half middle strip. Okay, now negative moment at the interior support. So this is your interior support. uh, we will over here it is going to be C, and over here again it is going to be uh, A, or you can say see if this is an exterior support, then it will be A. Over here it will be C. Okay, if it is the interior support, then here it will be D. Okay, let me show you the figure. Right. Okay, so C, D, or it can be anything. Okay, this both are interior. This is the interior support. You will have a moment over here, and you will this is a hogging moment over here, this is a hogging moment over here, right? So now we are talking about the interior support, negative moment at the interior support, right? So these are negative moments, right? So in general, for the negative moment at the interior support that is distributed, uh, whatever moment you get from the design, 75% will be transferred to the column strip, and 12.5 and 12.5% will be transferred to the two half middle strips, right? Okay. Now positive moment for all spans, whether it is an interior panel or exterior panel. Okay, this is applicable to all spans. So the column strip will take up 60% of the ammo, that is your sagging moment at the midspan. Okay, 60% will go to this column strip, and 20% to the half middle strip, and another 20% to the another half middle strip. Okay, so this is how the moments are distributed to the column strip and middle strip, and for this moment the half middle strip and the column strip are designed. Okay. 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 That is okay. Let me go forward. Drops. The drops, when provided, shall be rectangular in plan and have a length in each direction not less than one third of the panel length in that direction. For exterior panel, the width of the drop at the right angle of the non-continuous edge and measured from the center line of the column shall be equal to one half the width of the drop for the interior panel. Let me explain what does this means, right? Uh, so this is the minimum dimension required for the drop. So for an interior drop, okay, this should be x1 plus x2. Okay, this is L11, this is L1. So x1 should be greater than L11 by 6, and x2 should be greater than L1 by 6, right? So this is how you get this length, and this should be greater than y1 plus y2. Y1, this is L2, this is L2 1. So y1 should be greater than L2 by 6, and y2 should be greater than L2 1 by 6. Okay, so this is how you get the minimum dimension of the drop, right? Now in case of exterior drop, this should be x3. Okay, this should be x3. Fine. So x3 is should be greater than x1 plus x2 divided by 2. Okay, this is x1 plus x2 divided by 2. x3 should be greater than x1 plus x2 divided by 2 plus the half the column width, right? Similarly, y3 should be greater than y1 plus y2 divided by 2 plus half the width of the column, right? So this is the minimum dimension required to be given to the drop. Okay. Okay. So proportioning of slab thickness. In case of slab, the depth is governed by the deflection. For this purpose, the code recommends effective length by D ratio, referring clause 31.2.1 for IS 456 2000, right? And so this is which something which you know. In case of slab, deflection is governing factor. That is, depth is governed by the deflection, and these are some standard L by D basic ratio given to us for up to span 10 meters. Okay, then we can find L by D allowable, that is equal to L by D basic into KT into KC. Okay, so where KT is the modification factor uh, corresponding to the percentage of tensile steel, and Kc is the modification factor corresponding to the percentage of the compression steel, right? Okay, okay. So for the purpose of calculating the modification factor Kt for tension reinforcement, an average percentage of steel across the whole panel should be taken. Okay, in the case of our in case of standard two-way slab, we take 1 meter strip design, right? And we take the tensile steel in the 1 meter strip which we get, okay? But in case of flat slab, you have to take the average percentage steel for the whole section, okay? So this is your half column strip, this is your half column strip. Oh, sorry. This is your half middle strip, right? This is your half middle strip. This is your column strip. We can see that the steel in half middle strip, both the half middle strip is less, and the steel in the column strip is more, right? So that is why we will have to take an average percentage of the tensile steel for the whole cross section. That is what code says, okay? For slabs with drop confirming 31.2.2 span to effective depth ratio given 23.2 shall be applied directly. Otherwise, the span to effective depth ratio obtained in accordance with a provision in 23.2 shall be multiplied by 0.9. Okay, so the code says that if you are following these rules and regulations, then you can use these values. Okay, but if you are providing the dimensions of this drop lesser than this, then this has to be multiplied by zero point 0.9. That is what code says. Okay. The minimum thickness of the flat slabs will be 125 mm. The minimum thickness of the drop panel to be provided should be as shown below in the figure, right? So this is your thickness of drop panel. This is the thickness of the flat slab. This is distance x, right? That is from the edge of the capital to the edge of the drop. If there is no capital, then the distance x will be from the face of the column, and this should not be greater than thickness of slab plus the x by 4, right? And this offset should be greater of thickness of slab divided by 4 or 100 mm at least, right? That is what I have explained over here. Effective depth of drop shall not be exceed the thickness of slab plus x by 4. Okay, that is what I explained over here. The effective depth of drop shall not exceed the thickness of slab plus x by 4 plus the effective cover. However, the projection below the slab, this is the projection below the slab, should not be less than one fourth of the slab thickness, but not less than 100 mm in any case. Okay, so that is what the code says over here, right? Okay, now coming to the column capital, right? Uh, Column capitals are considered to be part of column. The flaring of the column at the top is generally done such that the plan geometry at the column head is similar to that of the column. The purpose, first let me explain what is this, right? Say suppose uh, we are having a square column, then the plan of this capital head should be square. If we are having a rectangular column, then the plan of this capital head should be a rectangular. If we are having a circular column, then this the shape of this capital should be circular in plan, right? If you are having a hexagonal column, then the shape of this capital in plan should be hexagonal. Okay, so you have to keep the geometry same. That is what the code says, right? Okay, now uh, for the purpose for providing column capital is to increase the punching shear capacity of the slab. Okay, say when there is no capital, right? The slab is directly rested on column, then the critical section will be at a distance d by 2, and the periphery length which resists the punching shear stress will be small. Okay, now if you increase the diameter of the column, which is known as capital, okay, if you flat the column, then the critical section to be taken for the punching shear will be at a distance d by 2 from the capital, right? So over here we will get a larger periphery which will resist the punching shear stress. Okay, so the purpose of providing this capitals is to increase the punching shear capacity of the slab. Okay, where column head are provided, the that portion of the column head which lies within the largest right angle cone or the pyramid less that has a vertex angle of 90 degrees and can be included entirely within the outline of the column, and the column head shall be considered for the design purpose. Okay, so code says you may provide any shape of your capital. Okay, but the angle, this 90-degree vertex angle, okay, the area within this is only to be considered for the design. Okay, so the area inside this dotted line will only be considered in design. The area outside this dotted line will not be taken in design. Okay, that is what the code says. Transfer of shear moment at the to the continuous beamless flat slab, right? Okay, after obtaining the design moment using either direct design method or the equivalent trend method, the unbalanced moment at the support are needed to be resisted by the column above and below the slab in proportion to their relative stiffness, right? So this is our panel. Okay, this we have a column over here, 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 and these are the moments which we get from DDM. Okay, this is your exterior moment, this is your interior moment, this is the moment near the support. Okay, so over here we have sagging moment 430, over here we have sagging, sorry, over here we have hogging, this is a hogging moment, right? Over here we have hogging moment 430. Over here we have hogging moment 407. So the difference between these two is known as unbalanced moment. That is 22.189. Okay, that is what we get over here. Now this unbalanced moment has to be transferred to the column. Okay, that is column above the joint and below the joint, and that moment will be taken by this column as according to their stiffness, right? Okay. But in case of flat slab, the transfer of unbalanced moment mu, this is mu, okay, from the slab to column takes place partly through direct flexure and partly through development of non-uniform shear stress around the column head, which will be added to the punching shear stress. This is very important. This is very important. Okay. Okay, this moment is not directly transferred to this columns through flexure, but it is partly transferred to this column through flexure and partly through shear, right? Okay, so in this figure, we see this shaded portion. This strip will transfer part this is the formula. Okay, the unbalanced moment transferred by flexure is lambda into mu, right? So lambda is found by this formula by c1 and c2. C1 is the dimension of column or capital in direction of the moment, and c2 is measured in transverse direction, right? This is c1, this is c2, right? So this moment, okay, is transferred by this strip to the column through flexure, right? So you can see this moment is transferred through flexure, right, over here. Okay, and now the remaining balance moment is transferred by shear, that is 1 minus lambda into mu is transferred by shear, right? Okay, so we know this portion is assumed to be supported on this imaginary torsion member, right? So this moment is this moment which will this is a twisting moment for this, right? This is imaginary torsion member, right? This moment will twist this member. Okay, and due to this twisting you will have shear force, you non-uniform shear force over here. Okay, so this non-uniform shear force is due to this twisting moment, that is due to this twisting of this torsion member, right? So this moment will be transferred to this column through this non-uniform shear. Okay, so this is how we the moments, unbalanced moment, are transferred to the column. Okay, so this is very important. Okay, Uh, the effective width of the slab through which the moment MUB is transferred to the column is taken as C2 plus 3D, right? Okay, fine. Load on the edge beams, right? Okay, so over here we can see at the interior joint the unbalanced moment will be not very high, okay, because we have a hogging moment over here, we have a hogging moment over here, so only the difference will be the unbalanced moment, but at edge the twisting moment will be very high, okay. So this is 263.62 as compared to 22, right? So over here it is better to provide a edge beam, okay, which will take this twisting moment, okay. So code suggests as per clause 31.3.2, bending moment in panel with marginal beam or walls, right? Okay. Uh, uh, where the slab is supported by a marginal beam with a depth greater than 1.5 times the thickness of the slab or by a wall, then, okay, the depth of this edge beam should be greater than 1.5 times the thickness of the slab, okay. So what load this, for what load this beam has to be designed, okay. So direct load falling on the beams, okay. Total load to be carried by the beam or wall shall comprise those load directly on wall or beam, okay. Say load of wall or self weight or any other load which is directly falling on the beam plus uniformly distributed load equal to 1/4 of the total load on the slab, okay. That is, this load plus UDL equal to 1/4 of the total load on the slab panel. So this is your exterior slab panel. So find the total load, capital W, okay, which is falling on this beam, and 1/4 of that has to be transferred, has to be converted to UDL, and that has to be taken on this beam, right? So the load that has to be taken on this edge beam is direct load falling on the beam plus UDL equal to 1/4 of the total load on the slab panel, okay. Now second point, what, for what moment this half column strip should be designed, okay. The code says the bending moment on the half column strip adjacent to the beam or wall shall be 1/4 of the bending moment for the first interior column strip, okay. This is your exterior panel, this is your first interior panel. So whatever design moment you get over here, and this half column strip should be designed for 1/4 of this design moment over here. This is a column over here, right? And so whatever moment you get over here, 1/4 of that moment has to be taken for the design of this half column strip. Similarly for this half column strip, okay, fine. Now torsion in edge beam, okay. Now this beam has to carry this vertical load as shown over here, plus it has to carry the twisting moment, okay. So this is a moment which we got over here, 263.62. So that moment, that is our exterior moment, right? That moment has to be distributed equally, uniformly throughout the edge beam, that is L2. Length of the edge beam has to be taken as L2, right? Okay. The edge beam has to be designed as a spandrel beam, and it may be assumed conservatively that the entire negative design moment MO exterior is uniformly distributed over the entire transfer length L2. Okay, so this, for this twisting moment and this load, this edge beam has to be designed. Okay, okay. Moments in column. Okay, okay, fine. So one is the unbalanced moment mu, which we got from the analysis. Code is given another formula. As per clause 31.4.5.2 IS 456 2000, at an interior support, the supporting member above and below shall be designed to resist the moment m given by the formula following equation, indirect proportional to the stiffness in case of DDM. Okay, so this is your interior column, right? Code, this clause is for the interior column, okay. Okay, so code says find the moment using this formula. If this moment is found to be less than mu, then take mu as a m. If this moment is found greater than mu, then take this as m. Okay, then this will be distributed to the column above and below as according to the stiffness, right? Okay, over here alpha c is sigma kc divided by sigma ks. Sigma kc is sum of stiffness of column top and bottom. Sigma ks is sum of stiffness of slab on this side and this side, right? Why? WD and WL are the dead load, design dead load and design live load on the longer span, right? W dash D is the dead load on the shorter span. Ln is a clear span between the columns for the longer span. L dash N is the clear span between the columns for the shorter span, right? Say if the spans are same, then your ln will be equal to l dash n. Okay, simple, right? So if this is only applicable when this when the span are different, right? Otherwise, if the spans are equal, then your l n will be equal to l dash n. Okay. Okay, so this is how do we transfer uh, the moment to the columns? How the unbalanced moment is transferred to the column? That is what we have studied. Part is transferred through flexure and part is transferred to shear. Okay, so that is what we have studied. Effect of pattern loading on slab moment, right? Okay. In case of design of flat slab using direct design method, and the live load and dead load are applied to all the span. That is what we studied. Okay, that dead load and live load is applied to all the spans. This load combination may not give you the most critical positive moment because to obtain the maximum positive moment, design live load should be applied on the alternate span. Okay, when we get maximum positive moment when we apply live load on alternate span, but here we are applying on all the spans, right? So there are chances that the moment positive moment which we get over here may not be critical, right? So to overcome this, code is given us a suggestion that when your alpha c, okay, this is a alpha c, okay, alpha c, this is alpha c, right? When your alpha c is found to be less than alpha c minimum, okay, then you have to find a factor beta c, and which has to be multiplied with the positive moment for the considered panel, right? So this is the formula for finding beta c. Okay, this is given in the code, right? Fine. So question arises in our mind that is there any factor to be multiplied with the negative moment? Okay, no, there is no factor that is to be multiplied with the negative moment. Negative moment need not be increased. Okay, because there is no likelihood of significant increase in negative moment at the support because to obtain maximum negative moment, design live load is applied on the adjacent span which we already are applying. Okay, so that is why no factor has to be multiplied with the negative moment. Whatever negative moment we get from the analysis can be taken directly, but for positive moment we have to check whether alpha c is less than or greater than alpha c minimum. Okay, so alpha c minimum can be found from this table 17. Okay, from this table we can see that if your imposed load by dead load is less than equal to zero point 0.5, then alpha c minimum is 0, right? But if it is greater than zero point 0.5, then you will have to find alpha c minimum. So let me explain you with an example. We have say ratio of L2 by L1. L2 is the transverse span, that is width of the slab beam member. L1 is the center to center distance between the column. Okay, if this ratio in our case this ratio is 0.6, so and our imposed load to dead load ratio is 0.8. 0.8 is greater than zero point 0.5, so so we will have to find alpha c minimum, right? So first we will do the interpolation for this. Okay, for 0.6, 0.6 falls between these two, so for the zero point 0.5 it is zero point 0.6. Okay, for zero point 0.8 it is zero point 0.7. You can find through interpolation alpha c minimum is 0.633. Okay, so now we have to do interpolation for this, right? So our imposed load by dead load is zero point 0.8. So this falls between this, right? Zero point 0.5 and 1. Okay, so when this is zero point 0.5, alpha c minimum is 0. When this is 1, our alpha c minimum is 0.633. So for zero point 0.8 we get this 0.7398. So we have to take list of these two. So list of these two is 0.798. So our alpha c should be greater than 0.798. Okay, if it is not found to be greater than zero point 0.3, our alpha c should be greater than 0.3798. Okay, and if our alpha c is not found to be greater than 0.3798, then we will have to find beta c, and we have to multiply that beta c for the corresponding positive moment for the selected span. Okay, fine. Now, one-way shear for column supported two-way slab. So the theory remains the same. Okay, we know that in case of one-way shear, we have to take a section at a distance d. Okay, I have taken three cases over here. This is simply column without any drop or capital. This is column where there is a drop. Okay, and this is column where there is a drop and a capital, right? So over here, simple, you have to take a section at a distance d. Over here, we have to check for two sections. One is take at a section at a distance d1. Okay, d1 is the effective depth of the drop panel. Okay, another you have to take a section at a distance d, where d is the effective depth of the flat slab. Right. Over here also, you have to take two sections. One is at d1, where d1 is the effective depth of the drop panel, and you have to take a section D from the drop over here. Over here you have to take from the column, from the face of the column. Over here you have to take from the face of the drop. Over here you have to take the section from the face of the column. Over here also you have to take the section from the face of the drop, right? So over here the effective depth that is to be taken is the depth of the slab, right? So section 1 1 is the critical section for one-way shear at a distance d1 from the face of the column. Section 2 2 is the critical section for one-way shear at the distance d from the face of the drop panel. Okay, and d and d1 are the effective depth for flat slab and the drop panel, right? Simple. So you can take 1 meter strip over here. Now ln is nothing but the clear distance between the column. Over here ln will be the clear distance between the column and the capital. Okay, fine. So this red line are the center line of the panel. Okay, so you can find this length easily, right? So for finding the shear, okay, v1 is the shear acting over here for this strip. So length of this strip into 1 meter into w, that is your v1. Okay, so this cross section I have shown over here, right? So v will be acting over here. This is v, and this is a section which will resist the shear uh, shear, right? So the area of this section is this is 1 meter, so this is 1 meter, and effective depth d. So this is the area which will resist your v, right, over here, right? Similarly, this is for v2. Okay, the shear force over here is v2. So simple, length into 1 meter into w, that is your v2, right? Simple. Okay, okay. So shear force, once you have found your shear force, you can find the nominal shear stress, that is V divided by this area, right? So that is what is written over here. Okay. So when you are taking 1 meter strip, okay, for a check for one-way shear, then you will have to take 1 meter strip in column strip region, and also 1 meter strip in half meter strip region. Okay, and this is the permissible shear stress tau c formula, K into tau c, where tau c can be found from table 19 of IS 456 2000. Okay, for the corresponding percentage of steel, right? So the over here, if when you're using you're taking in account 1 meter strip, then whatever the percentage of tensile steel you have at this section has to be taken in account, right? Fine. K is obtained from this table. If your flat slab thickness is greater than 100, then it will be 1. Otherwise, according to the thickness of the flat slab, you have to find K from this table. Okay, and your nominal shear stress should not shall not exceed half the appropriate value of tau c max given in table 20. Okay, so this is tau c max given in table 20. For solid slab, you have to take 50% of this, right? Then our flat slab is a solid slab. That means tau b should be less than 0.5 tau c max in case of solid slab. Okay. For finding the permissible shear stress, you need to find the percentage of shear. So simple. This is one way shear section at a distance d from the face of the column. Whatever percentage of tensile steel you get over here, for the corresponding percentage of tensile steel pt, you have to find tau c from table 19. Okay. Okay, the critical section for one-way shear for a slab carrying uniformly distributed load in column supported slab is located at the distance d from the face of the column. A capital bracket as shown in figure above. The shear stress may be computed taking the full width of the strip L2. Okay, instead of taking 1 meter strip in column strip and 1 meter strip in half middle strip, you can take the full width. Okay, that is L2. Okay, you can also find the shear force for the total width of the slab beam. Okay, simple, nothing, everything remains the same. Instead of 1 meter, you have to change this to L2. That's the width of the uh, slab beam member, right? And when you are taking L2, then you have to take the average percentage of tensile steel as shown above. Let me show you the figure again for finding PT. Okay, oh yeah, right. When you are considering the whole width L2, then you have to again take the whole PT average PT, right? You have to take the average PT percentage of steel for the whole width of the panel. Okay, so that's what you have to remember. Okay, so this is how we do the check for one mesh here. Okay, it's very simple. uh, so let us move forward. uh, okay, so this is very important. The thickness of slab is usually governed by deflection criteria. Most of the time the slab are found to be safe in one way shear. Okay, so one way shear is not a big tension in case of design of flat slab or our conventional one way or two way slabs, right? uh, Now, two way shear or punching shear, this is very critical in case of flat slab. In case of flat slab without beam directly supported on column undergoes punching. This is why punching shear failure is very critical in flat slabs. The punching failure is somewhat truncated shape of a pyramid as shown in figure below. This is your punching shear crack, right? This is your truncated portion, right? The critical portion of the punching shear stress is taken at a distance d by 2 from the face of the column, capital or bracket. Yeah, in the figure below, shaded portion shows the area of concrete which resists the punching shear stress. Okay, so we take it critical section at a distance d by 2 from the face of column, bracket or capital, right? So this shaded portion will resist the punching shear stress. Okay, so this is the permissible punching shear stress as per IS 4.6 2000, that is Ks into tau c. Ks is 0.5 plus beta c. Where beta c is not greater than 1. Beta c is ratio of shorter side to the longer side of the column or capital. Tau c is 0.25 into under root fck. And nominal punching shear stress is found by V punching divided by PO into D. Okay, PO is the periphery, okay, into D. Okay, this is D, right? This is D. Okay, so this is the nominal shear stress. Okay, tau B should be less than tau C. Okay, so I have taken 4 cases over here. This is a column where there is no drop, no capital. This is a column where there is a drop. This is a column where there is a capital. This is a column where there is a drop and there is a capital, right? Simple. So you have to take a section at a distance d by 2, right? So this is the critical section for punching shear stress at a distance d by 2 from the column, right? From the column. Over here there is a drop, so critical section at a distance d by 2, distance d by 2 from the drop. Okay, this is capital, so critical section at a distance d by 2 from the capital, right? This is from the capital. Okay, and over here you will have to take two critical sections. One is at a distance d by 2 from the uh, capital. Okay, this is capital, right? This is at a distance d by 2 from the capital. Over here we will have to take one section at a distance d by 2 from the capital, and another section at a distance d by 2 from the drop. Okay, d by 2 from the drop. So you can have such four cases in practical field. Okay, simple. So case 1, case 2, case 3, case 4. This is case 1, case 2, case 3, case 4. uh, Column length is c1, column width is c2, drop length is l, drop width is w. This is column capital length is cl, column capital width is cw. Okay, and so on. Okay, so what you have to do is find the length of this periphery, right? So for case 1, this is the length, right? For case 2, this is the length. For case 3, this is the length. Over here you have two cases. This is case 1, that is around the capital, d by 2 around the capital. Okay, that is periphery you get using this formula. And this is the critical section periphery po around the drop, you can get by this formula, right? So once you know your periphery into effective depth d will give you the area which will resist the punching shear stress. Okay, so that is what you get this, right? Now we have to find v punching. Simple, nothing. I have made a table over here: case 1, case 2, case 3, case 4. Okay, so you have to find the load area. This is the load area here, right? So for finding the shear in case 1, okay, case 1, find the total area. This is A into L2. This is L2, right? Mm, Minus this unshaded area into W. Okay, W into A into L2 minus unshaded area inside the critical section, right? That is going to be shear force for case 1. For case 2, this is B into L2. So, okay, B into L2 into W minus uh, this area. Okay, unshaded area inside the critical section, right? Similarly for case 3 and case 4, okay, you can find shear force. Okay, and this divided by uh, this will give you the nominal shear stress. Okay, right? So usually your tau v should be less than tau c, right? But if your tau v is found to be greater than tau c, but tau v should in no case should be greater than tau c maximum, right? The tau c maximum is equal to 1.5 into tau c. Okay, so when this is the case, then you can provide shear reinforcement like this, right? Shear, you can provide shear reinforcement like this. So this is the picture of this shear reinforcement, and when you view this from this side, it is something like this. Okay, so I hope you must have find this video useful. Please visit website mmsprogramcivil.com for all the education videos. Please watch the video for design of flat slab where a complete example is solved, which is uploaded on website mmsprogramcivil.com. Thank you.